Now there's one more analogy that is especially important and especially important to very deeply understand, and that is what is torque. Now in linear motion we had forces, now we have torques. Torques are different than forces, okay? They're like a force. A torque will cause, like a force will cause something to accelerate linearly. A torque will cause something to accelerate rotationally. But torques are more than just forces. Torque is another moment. It has something to do with distance. So, for example, how hard am I spinning this thing when I pull in the direction of my thumb, that way? So I'm pulling this away. How good of a job does that do to spin this? Not at all. Pulling out that away doesn't spin it at all. Which way do I want to pull or exert a force to get this thing to start accelerating rotationally? So you might think, okay, which way do I want to do it? This way does nothing. This way does the most. If I push this way, I get the most out of it. If I have a slight angle that way, like if I pull the way my thumb is, I do get a slight torque, but if I want to exert most of the torque, just tangentially, if I exert that force, I get the most torque out of it. So apparently, there's a couple things that matter, and here's another example of something that matters. Will I get more torque on this if I try to push up at this point, or if I try to push up at this point right here? Which is going to be easier to get this thing accelerating? Pushing it up right here or pushing it up right here? Now you may guess, if you've ever tried to unbolt something, that the farther you are from the axis of rotation, the more torque you get. In other words, if I do this, it's a lot easier than trying to do this. And you must try this in the lab. You actually have to feel how this feels so you get an idea of it. So this is easier than this. So apparently the torque amount depends on not only the amount of force, how much force I'm exerting, but the angle of the force. Pulling out this way does nothing. Pulling this way does a lot. And also the distance from the axis of rotation, the displacement. So R comes into play again here, but R means something different. In this case, what we have is a bolt right here that's being turned by a wrench. I'm exerting a force out here at the end, and R is the distance from the axis of rotation, the displacement from the axis of rotation, to the point of force application. R for torques means something else. R means the displacement from the axis of rotation to the point of force application. That is such, you got to know that rhyme. You really have to know what R is. Otherwise, there's all kinds of distances given in problems. You're not going to know which one to pick. So for masses, moments of inertia, R is the displacement from the axis of rotation to the point where the mass is stationed. For torques, R is the displacement from the axis of rotation to the point of force application, which in this problem is right there. Now, so to figure out the torque, you've got to take the R value, this value right there, and you've got to multiply it by the force. This got to multiply it by the force that way, but notice that the angle also matters. And theta is the angle between the R vector and the F vector. This actually out here is theta right there. Because notice that if you want to figure out the angle between two vectors, to figure out that angle between two vectors, you've got to take the vector. Here's the R vector right there. It does point that way. You've got to put them tail to tail. So I'd have to lift this vector up and move it. Let me see if I can actually do that. I'd have to lift this one up and then move it over to there so the vectors are tail to tail. And then I can find out the angle between them, theta. That is an important concept. As we'll see, torques are very forgiving in terms of your calculation. So here is the definition of torque. The magnitude of the torque is R, the distance, displacement from the axis of rotation to the point of force application, times the force itself, times the sine of the angle between them. And again, to figure out that angle, you do need to put the force and displacement vectors tail to tail to get that actual angle. So R times F times the sine of the angle between them. Now the direction, this torque actually it has a direction. It is a vector. And another way we write this is this. This torque is the cross product between R and F. I'm going to just write that right here. Torque is defined as R cross F, which just means RF sine theta, and the direction is determined by the right-hand rule. We'll practice that. We're not going to use that this much during this chapter. We'll use the cross product direction a lot more. Right now, we're just going to either say the torque is clockwise or counterclockwise, but that actually does have a specific vector direction, as mentioned before. For example, for you, this is clockwise. That would be a vector towards me. Counterclockwise this way would be a vector towards you. So this is called the cross product or vector product. And it's kind of the opposite in many ways as the dot product. And let's just do a quick comparison of these two. Notice that the dot product, A vector dotted on B vector, the magnitude is AB cosine of theta. And a way that you could write this is just A parallel times B. The component of A parallel to B
times B
is a magnitude only. The cross product, A crossed on B, is equal to AB, the magnitude is AB sine theta, which is A perpendicular times B, and it is a vector. And the vector direction, it is a vector. We'll do some things to figure out the vector direction. The dot product produces a scalar. So we'll play around with this a little bit right now. Again, we won't need this until later, but it's useful to kind of just somewhat familiarize ourselves with it. So here is some cross product practice using the right-hand rule. For the right-hand rule, what you do is you take your fingers and point them in the direction of the R vector, or the first vector in the cross product, and then you bend your fingers in the direction of the second vector in the cross product, and your thumb will point in the direction of the cross product itself. Now, cross product is not commutative, so R cross F is different than F cross R. In fact, they're in opposite directions. So you must have it in the correct direction. In the correct order. Let's go ahead and try this, and I'll show you how to do it. So what I have right here is, first, let's say I have something on a mass on the end of a string, or it's on a massless disk right there. It's R, the distance from the axis of rotation to where the mass is stationed, is that away, pointing to the left on the screen here. And the force is perpendicular straight up. So what you do is, R is this way, that away. And now what I got to do is figure out how can I bend my finger so that it doesn't hurt in the direction of F. Now, if you go like this, ow, ow, physics hurts, but it shouldn't hurt that much. So this cannot be the right way to hold my hand. Doing this way also hurts. Oh, wait, if I hold it this way, I can do fingers in direction of R, bend the fingers in direction of F, and then my thumb points in the direction of the torque. That torque, which is a clockwise torque, can be expressed as a vector towards me. Finally, if let's say the R vector is like this, okay, then I've got to do R cross F, bending it just slightly in the direction of F. My thumb points into the page. So in this situation, I'll go ahead and draw these. In this situation, the torque vector is into the page. So the torque vector is like that. That's what the torque looks like, into the page. Now, if you want to actually figure out the magnitude of these, R cross F, that's the torque, equals the magnitude of it is RF sine theta. Put the R right over here. So we get that angle theta right there. In order to figure out the angle between two vectors, you must put them tail to tail. Now, the good news is that sine of theta is very forgiving. If you measure the wrong angle, let's say instead of measuring the correct angle theta, you measure this angle. Notice, so that's when you put them head to tail, you get that angle. It is true that the sine of, I'm going to call this phi, this angle phi, it is true that the sine of theta is equal to the sine of phi, which is the, that would be the complement or the supplement of theta. It is true that the sines of those angles are the same. So if you screw up and use the wrong angle, the tip to tail angle, you'll still get the right numerical answer. But conceptually, it is important to understand that the angle you're truly trying to get at is the angle between the vectors is when you put them tail to tail. Now, back to this diagram, there's one more very, very useful distance that we have here. And that is what is called the moment arm, or also called the lever arm. And that is right here. This is what we call the moment arm or lever arm D. And what that is, if you just extend the force line, this is called the line of action of the force. You can extend it in both directions infinitely. This is the line of action of the force right here. That's the line of action of it. You just extend that force vector infinitely in both directions, you have the line of action of the force. If you just find the shortest distance between the axis of rotation right there and this line of action, you have what is called the moment arm or lever arm. And that's incredibly, incredibly, incredibly useful. You will notice that this happens to be equal to r sine theta. And that's another way to look at it, because we can actually express the torque in a couple of different ways. Let's go ahead and do that right now. For example, torque we can express as r cross F, and the magnitude of that, the magnitude of torque, is rf sine theta. Or you could express the magnitude of the torque like this: r times f sine theta. Notice that this component right there, that's just the r, the distance from the axis of rotation to the point of force application, that's r, times this would just be considered the component of force that's perpendicular to r. That's what f sine theta is. Notice that in dot products, it was only the parallel components that mattered. Here, it's the perpendicular components that matter. There's yet another way to express the magnitude of the torque, and that would be r sine theta times F. But that is equal to the lever arm times the force. And oftentimes, or many times, the lever arm, this is right here, that and that, that's what we call the lever arm, or sometimes called the moment arm. But that, as we'll see with practice, is another often easy way to figure out what the torque is. And again, I've got a rhyme for this, of course. I've got to have a rhyme for everything. Lever arm, or D, can be thought of, and here's a little rhyme, the shortest route of transportation to the line of action from the axis of rotation. Notice that there is no shorter distance from this axis of rotation right here. There's no shorter way to get to the line of action than D. Notice that it will always be a perpendicular to the line of action of the force. So this will come in handy, believe me.